Today we will learn about fresnel laws, polarization by reflection and total reflection. Fresnel has given certain laws for polarization, and on the basis of these laws we used to explain reflection and transmission of electromagnetic waves at boundaries. We will get a brief idea about these in this lecture. In the last lecture, we have discussed reflection and reflection at boundaries. But when we discuss reflection and reflection at boundaries, we will take care about the polarization component as a light is a transverse wave. So we will discuss here about this. In this lecture, we will learn about Fresnel equations and their application in obtaining boundary conditions for electric and magnetic field. The reflection of electromagnetic radiation involves returning or throwing back of the radiation by a surface. Whenever we send a light or electromagnetic wave, then it will be reflected back or thrown back by the system. But in that reflection, what kind of wave is there? Is it a polarized or unpolarized? That is given by the Fresnel. I think all of you know this, then light is a transverse wave. It means whenever light propagates, it vibrates perpendicular to the direction of propagation in all the directions. But polarized light means light can vibrate only in one direction or in a particular known direction, and others are prohibited. A reflecting surface is generally the boundary between the two materials of different electromagnetic properties. One different electromagnetic property may be refractive index or any other. The device designed to reflect radiation are called reflectors or mirrors. The reflectivity of a surface is a measure of amount of reflected radiations. Anti-reflection coating are used to reduce the reflection from surface, as in the case of glasses, specs we use on some other applications. I think all of you know this. When light propagating in a uniform field encounter a smooth surface, which is the boundary of another medium of different refractive index. Here I have shown a k vector of a particular vector of incident light, and this is a boundary. Now refractive index is shown by this incident refractive index, and this is transmitted refractive index. And due to this, at the boundary, we need to define some terminology before studying Fresnel laws. Here in this, now we are defining plane of incidence and plane of interface. A propagation of light towards the reflecting surface is shown here, and this surface is reflecting surface. The surface is reflecting surface. The light is propagating through here. This is, and from there it is reflecting and moving to this direction. And this here, this is the normal to the surface. Now if we take these three, incident, reflection and normal, then these three form plane of incidence. Plane of incidence basically is a YZ plane that contains incident and reflecting k vectors. If we want to define the interface, plane of interface, then it is the plane, an XZ plane. This define interface between the two materials. And here this is reflecting surface, a plane of interface between the two. A question, and very interesting question. Which way is the E field pointing? This is very important question for E field. E field have two possibilities. One is called S polarization, which is equal to perpendicular polarization, S is perpendicular polarization, and stick up out of the plane of incidence. Stick out of the plane of incidence. That is called S polarization. Here, here the plane of incidence is the plane of diagram, and this is plane of interface, and line incidenting and reflecting, and you are having sticks up to the plane, whereas p polarization is plane to the parallel to the plane of incidence. So one is parallel to the plane of incidence, second is perpendicular to the plane of incidence. We have assumed here a plane of incidence. Here this is perpendicular distance, and if you assume the same plane here, then this is in the plane. These are the two difference for two types of electric field we are having wire incident. Here we are ignoring magnetic field. Same behavior will be given a magnetic field, but in most of the calculation we use electric field. In this figure, this concept is more clear. Suppose light is incidenting here. This is your incident light. Then this light has two components. One is X component, and there is P component. As we told in the last slide, S is perpendicular to the plane. That plane is here. This is plane of incidence, and this is parallel to S is parallel and P is perpendicular. Now, it is strike here and reflected. The reflected will have both again. Number one, and number two, intensity may vary. You are observing here high intensity in the incident side and very less in the opposite side, and obviously this is reflecting surface. The amount of reflected light is different for two different incident polarizations. Yes, it also depends on these angles. Fresnel discussed, analyzed S and P polarization and studied what happened when electromagnetic wave strike on any surface, dielectric surface. Fresnel has given these equations in 1820, so about 200 years ago, and we treat the case of S polarization first. First we are taking perpendicular electric field, then we will take perpendicular parallel electric field. So this component is there, light is incident, k vector is incidenting, and we are having electric field which is perpendicular, and magnetic field obviously perpendicular to that incident. And after this incidence, you are observing here EI and BI, electric magnetic field. This is the interface. Beam geometry for light with its electric field is taking up out of the plane of incidence. We are say using. After reflection, the angle will be theta r, and now the BI, in place of BI we are having BR reflection and ER, and the reflected K is KR. If something is transmitted, then it is BT, KT and ET, and this XY plane is basically interface plane. For analysis, we have some boundary conditions for electric field at an interface. The tangential electric field is always continuous. In other words, the component of E field that lies in the XZ plane is continuous as you move across the plane of interface. All fields, E fields in the Z direction, which is in the plane of interface. So, EI plus ER should be equal to ET at y is equal to 0. We are not explicitly writing the x, y, z, y, x, z and t dependent, but definitely it is there. Similarly, we can also apply boundary condition for magnetic field. The tangential magnetic field is also continuous. The total magnetic field in the plane in the interface is continuous, so all B are in xy plane, so we take x components. This is Bi, then Br and Bt. Bi we want to take, and since this is perpendicular, so we should take cos. Bi cos theta plus Br cos r should be equal to Bt cos theta t. We have concluded that EOI, E0I plus E0R is equal to EOT, and B0I cos theta I plus B0R cos theta I R minus B0T cos theta is equal to 0. But we know that B is equal to E C0 over N, or N E upon C0, and theta I is equal to theta R. If we use these values here, so theta is equal to r, then these cos theta will be same, can be taken out, and we will live with N EOR minus EOI is equal to N EOT cos theta t. If we also substitute this equation of EOT is equal to EOI plus EOR, we will get this result. And we left with these results. N EOR cos theta I is equal to this match. We can also obtain reflection and transmission for perpendicular polarized light. If we rearrange this, then Ni EOR minus EOI cos theta I is equal to NT EOI plus yields this. You just rearrange this. Now, if we solve this for EOI upon EOR upon EOI, this will called reflection coefficient. How much is reflected EOR upon EOI? Basically it is ni cos theta I minus nt cos theta t upon ni cos theta I plus n r cos theta t. Similarly, we can also obtain EOT upon EOI. It is called transmission coefficient, how much it transmitted. Both can be observed. These equations are called Fresnel equations. In exam, it may be asked, write down Fresnel equations. This is for perpendicular polarized light. Another part is Fresnel equation, parallel electric field. In case of p polarization, now we are talking about parallel electric field. EI and ET is there, and after reflection, this is your electric field. Here we are taking this as a parallel, electric field as a parallel and magnetic field as a perpendicular. So it is moving here, then finally reflected there. The reflected magnetic field must point into the screen to achieve E cross B proportional to K. Reflection and transmission coefficient can be obtained for parallel polarized light in the same way as we did in the past. For parallel polarized light, now this component BO component should be equal to BOI minus BOR should be equal to BOT, and similarly as we did for the cos, now electric field, this time we will did for electric field as previously we did for magnetic field cos component, because same we are assuming that now this is parallel, so we will do this. If we solve this for EOI, then we can get transmission and reflection coefficient. This is transmission coefficient and reflection coefficient, but this is parallel component. Now these equations are called Fresnel equation for parallel component, parallel polarized light. So now we have two similar results. Everything depends on what you are saying. Electric field, you are assuming electric field as a perpendicular or parallel. In this, we have summarized our results as polarized light and p-polarized light, and beautifully it is explained in the figures also. Incident wave, reflected wave, and transmitted wave. If it is parallel, whatever what interface is there, plane of incident, whether your electric field is in here in the first case, the electric field is not in the face which is perpendicular, and here we have shown the electric K vectors are black, so transmitted, incident, everything is shown here. And we have obtained the results for S polarized light and for P polarized light. And for both polarization, n sin theta is equal to n I sin theta is equal to n sin theta d. These two polarizations are indistinguishable at theta is equal to 0 degree. And total reflection at theta is equal to 90 degree for both polarizations. Zero reflection for parallel polarization at Brewster angle. There is no reflection for parallel polarization at Brewster. The value of this angle depends on value of the ratio Ni over Nt, and this is called Brewster angle, which was given by Brewster. We always discuss this Brewster angle whenever we that in the case of Brewster angle, zero deflection for parallel polarization, only perpendicular will be observed, no parallel. So this is one of the best method to create polarizers, to create polarized beam by put the light on Brewster angle. For air to glass, the Brewster angle is 56.3. So this is one of the method also. On the right hand side, we have plotted reflection coefficient and incidence angle. As we increase the incidence angle from 0 to 90, the coefficient, perpendicular component coefficient is decreases, or the parallel is in opposite direction, but at point it is 0, this point. And this point where this is 0, this is Brewster angle. If refractive index of glass is more than air, total interreflection above is critical angle, and that critical angle is equal to sine of inverse of sine nt over ni, 41.8 from glass to air. This is also called Sine's law. Sine in Snell's law cannot be greater than 1. And we have shown here that the reflection coefficient is moved in this way. The critical angle is for perpendicular continuously from 0 to increasing continuously, and this was equal to main direction. But at particular angle for parallel, the Brewster angle, that is called Brewster angle, when there is no reflection coefficient. After this, we have shown after 30° both sides we have shown total internal reflection at this angle, completely reflection. This you may take this as a the topic may be typical, looks typical, but you have seen many Fresnel equation in action many places. Window look like mirror at night when you are in brightly lit room. Suppose you are in a very bright room, then it looks like a mirror because of no reflection is more reflection is there. One-way mirror used by police to interrogate bad guys are just partial reflectors. Actually, very thin aluminum coating is there. That is one way. On one side it looks like a mirror, but the second side it is not. This Disneyland put growls next to you in the haunted house using partial reflectors. They can also be done. You can create many illusions. A smooth surface can produce pretty good mirror-like reflections, even though they are not made up of metals. These are the applications we use. Many lasers use Brewster angle components to avoid reflection losses. We choose in such a way mirrors design that it should be use Brewster angle. Optical fibers only work because of total internal reflection. This is very best property we are using. So in this lecture we have discussed Fresnel equations and use of this Fresnel equation to get reflection and transmission at boundaries. In the exam, the reflection and transmission results may be asked. Thank you.